Let's have a look at another problem where we are dealing with changing the variables for an ideal gas. In this problem, we are dealing with a balloon. The balloon is initially filled to a volume of 700 milliliters at 1 atmosphere and 273 Kelvin. And then it is cooled down to 100 Kelvin, and our goal is to calculate the final pressure of the balloon. So let's go ahead and label this as the initial conditions of our balloon, or actually I'm going to use the number 1, and this will be the final conditions of the balloon, number 2. And initially we have for our balloon, the initial pressure is 1 atmosphere. The initial volume of this balloon, the problem says, is 700 milliliters, which I'm going to convert to 0.7 liters. It doesn't tell us anything about how many moles we have in this balloon, so we're just going to write in. And the initial temperature of this balloon, it says it's 293 Kelvin. So these are all the variables that I took from right here. And then we have our final conditions for the balloon. So the final pressure of the balloon, that is what we are being asked to calculate. What is the final pressure of the balloon? The final volume of the balloon, it says that the volume of the balloon is kept constant. So that means that the volume does not change. It's staying at 0.7 liters. The final number of moles for the balloon, well, again, we don't know anything about the moles of the balloon, so we're just going to call that N. And the final temperature of this balloon, T2, is 100 Kelvin. So it's been cooled down to 100 Kelvin. So just like in the last problem and in this problem, when we don't know anything about one of the variables other than we know that it's not changing, we can just identify that variable not as N1 or N2, but just N. We could totally do the same thing with volume here. The volume variable does not change. It's not going to be necessary for us to know exactly what the volume is. So we can go ahead and replace that number for the volume with just the letter V. We can do that for the initial and final conditions as well. And again, this is going to be true anytime we have a variable that does not change from the initial conditions to the final conditions. First of all, we don't actually have to know what that variable is mathematically or numerically. And second of all, we don't have to use any 1 or 2 subscripts to go along with it. So in this particular problem, we have a pressure and temperature situation that's changing, and we're being asked to calculate the final pressure. There isn't an individual gas law that gives us the direct relationship between pressure and temperature. In the last video, I showed you a problem where we were just looking at a P1, V1, P2, V2 relationship. We could have just jumped straight to that equation. But in this situation, we don't have a relationship between pressure and temperature, which means we have to derive one for ourselves. So we're going to do that by starting with the ideal gas law, P1 V1 equals N1 RT1, and we'll do the same thing for the final conditions as well. P2 V2 equals N2 RT2. Now before we start plugging numbers in the last video we just started plugging numbers in at this point. Before we start plugging numbers in, let's go through and substitute our variables that don't have subscripts. So let's take care of those guys right there, our volumes and our moles. And instead of writing V1 and N1, we're just going to write V, P1 V equals N RT1. And we'll do the same thing on the other side as well. P2 V equals N RT2. So now the equations are looking very similar to each other. Our next goal is to take all of the variables that don't have subscripts, so our V and the N and the R, take all of these variables and lump them together on the same side of the equal sign. So what I'm going to do, I'm going to do this slowly on this side. I'm going to divide both sides by the volume. So I get P1 equals nRT1 over V. And then I'm going to divide both sides by T1, like that, and I will end up with P1 over T1 equals nRV. Now, if you're wondering why I just did that, let's do the same thing over here, and it's going to become clear. So I'm going to do the same thing over here. I'm going to divide both sides by V. So I get P2 equals nRT2 over V. And then I'm going to divide both sides by T2. So I get P2 over T2 equals NR over V. Now here are the two equations. This is where we're at. And notice that both of them have this identical term, NR over V. So we can say, I'm going to go to the middle now, we can say P1 over T1 equals NR over V, and that's for our initial conditions. And NR over V is also equal to P2 over T2. So again, just like we saw in the last one, we can just get rid of this whole term in the middle. It's not necessary anymore, and we've come up with a relationship between the variables pressure and temperature. Now, after we've done this derivation, we are now ready to actually plug in the values that we are working with. So our initial pressure, which is 1 atmosphere, and our initial temperature, 293 Kelvin. And again, these are numbers that I'm taking from here. And that is going to be equal to our final pressure, which is what we're trying to solve for, divided by the final temperature, 100 Kelvin. So to solve this problem mathematically, to solve for P2, we will go 1 times 100, and we will divide that by 293, and we get a final pressure of 0.34.